right, guys, welcome back. So today we are going to learn how to use the neutralization reactions that we learned from the last video and kind of layer them in with the idea of stoichiometry to do quantitative neutralization. This is an acid-base titration. Titrations are a way that we use in the lab to take a standard either acid or base and measure it against an unknown base or acid and find the concentration of that unknown base or acid. And we usually use that by two ways. We can either measure the pH as we add in acid and base and calculate the pH based on pH on the y-axis versus how much acid or base we add. And we can use the inflection point to determine where that volume equals the neutralization point, or we can use a color indicator. Indicators are things that change color at a certain pH, and we match that pH with what that pH of the reaction is so that we get a visual cue about when that neutralization point has been reached. Okay, so here are how we do some of these calculations. This is a lot like stoichiometry, okay, and we use the molecular equations for this. So you don't have to worry about doing the net ionics. We're just going to do straight double replacement neutralization molecular equations, okay? And remember, when we multiply molarity times volume, we get moles. Let me show you what I mean. Molarity is moles over liter, and volume is always given usually in milliliters, but we want it in liters. So the liters cancel, so we're just left with moles. Okay, so that's where we do kind of like we did with stoichiometry. We started with grams of what we knew, we went into moles of what we knew, and then we went into moles of what we wanted to know about, and we went back to grams of what we wanted to know about. Now we're going to start with volume and liters to get to moles. Use that mole relationship, and then we're going to get into moles of what we want to know about. And then we don't necessarily go back to grams. Sometimes we do, but sometimes we will go into liters or volume, or maybe even calculating the molarity of what we want. Okay, so it's the same process as stoichiometry, but we're using the units a little bit differently here. Okay, so example 12. What would the molarity of potassium hydroxide be if it was neutralized by 41.6 mils of a 0.1 molar nitric acid solution? Okay, so the first thing always is to write a balanced equation. So I have nitric acid reacting with potassium hydroxide, and these are all double displacement or double replacement reactions. So it's really important to be aware of the charges here. So hydrogen is a +1, nitrate is a -1, potassium is a +1, hydroxide is a -1. Hydrogen will get together with the hydroxide and make water. Neutral, right? Neutralization reaction. And potassium will get together with the nitrate, +1, -1, so it's just potassium nitrate. So this is a pretty easy reaction. It's 1:1:1:1 relationship. Okay, the next thing, we've got to figure out what do we both know a volume for and a concentration for. So we know a volume and a concentration for my nitric acid. Okay, now the next thing, my volume molarity is in liters, right? But my volume here is in milliliters. So there are 1,000 milliliters in a liter. So wouldn't you say that 41.6 milliliters, if I move that decimal place 3 places over, is 0.0416 liters? Could I do that little step to get it into liters? It can. Okay, so I'm going to start off with my 0.0416 liters of my nitric acid solution. Then I'm going to multiply it by my concentration. That means moles per liter. And I can use that to cancel out my liters. So I have 0.1 mole of nitric acid for every liter of that nitric acid solution that I have. So my liters cancel out. I'm left with moles. Now I have to look at my relationship. I have 1 mole of nitric acid reacting with 1 mole of potassium hydroxide. So my moles of nitric acid cancel out. I want molarity, which is moles per liter, right? I have a volume here, but it's in milliliters. So I'm going to do the same trick. I'm going to move the decimal place 3 places to get to my liters. So this would give me 0.151 or 6 liters. So I have 0.0156 liters of my potassium hydroxide. I have moles over liters, which gives me the units that I want. So let's see, I've got 3 sig figs. So when I do the math here, I get 0.26 repeating. So I get I get 0.26 repeating. So with 3 sig figs, this would be 0.267 molar potassium hydroxide. Now remember that capital M is moles per liter. Okay, so there we go. There's example 1. Example 2. What volume of potassium or sulfuric acid would be necessary to completely neutralize 25 mils of a 0.026 molar sodium hydroxide? Now, we need to create an equation. So, sodium hydroxide and sulfuric acid. Now, hydrogen, each of them is a positive 1. Sulfate is a negative 2. Each of the sodiums are a positive 1, hydroxide's a negative 1. So I've got 2 hydrogens. So that means I'm going to need 2 hydroxides. So I'm going to double this to give me 2 waters. And then I have the 2 sodiums, and I'm going to need the 2 sodiums to make the sodium sulfate. Okay, so there's my molecular equation balanced already. Okay, now I have a volume and I have a concentration on my sodium hydroxide. So I'm going to start with my volume and I'm going to make it into liters. So I'm going to move my decimal place 3 places over. So that's going to give me 0.025 when my computer will let me draw. So I'm going to start with 0.025 liters of potassium or of sodium hydroxide. Once my computer figures out what it's needing to think about. Okay. Super frustrating. I think the network is having a hard time. I know Canvas is crashed right now. So I think this whole thing is having a hard time. Okay, so this is going to be 0.0250 liters. So I'm going to start with that of sodium hydroxide. Now I've got this concentration That means I have 0.026 moles of sodium hydroxide in 1 liter. So my liters of sodium hydroxide cancel. Okay, now I need to look at my relationship. I have 2 moles of sodium hydroxide reacting with 1 mole of sulfuric acid, right? Okay, so I've got that relationship. And then I want a volume. So I can use this concentration right here to get me a volume. So I have 0.050 moles of sulfuric acid in 1 liter of solution. So my moles of sulfuric acid cancel out, and I'm left with liters. Okay? So when I do the math on this, I only have 2 sig figs, so I will get 6.5 times 10 to the negative 3 liters. If I want to make that milliliters, that would be 6.5 milliliters. Okay, so not a whole lot of sulfuric acid is needed there. All right, number 14. How many grams of calcium hydroxide are needed to neutralize 72.6 mils of 0.2 molar hydrofluoric acid? Equation. So calcium hydroxide reacting with hydrofluoric acid. I can already tell I'm going to have to double this because I'm going to make calcium fluoride, and I'm going to need 2 fluorides to deal with that plus 2 calcium because fluorine's a -1. And I'm going to need to make 2 waters. Okay, so there's my molecular equation. I'm going to once again get this into liters. So this will be 0.0726 liters of hydrofluoric acid. So I'm going to start off with my liters, 0.0726 liters of hydrofluoric acid. And I'm going to use my concentration. I have 0.2 moles of hydrofluoric acid in 1 liter of my hydrofluoric acid solution. So my liters of hydrofluoric acid solution cancel out. I have moles, and now I need to look at my relationship. So I have 2 moles of hydrofluoric acid reacting with 1 mole of calcium hydroxide. Okay, so my moles of hydrofluoric acid cancel out. And now I just need to go from moles to grams because I want grams. So 1 mole of calcium hydroxide. Let's see, calcium plus 2 oxygens plus 2 hydrogens. That will give me a molar mass of 74.10 grams of calcium hydroxide. So my moles of calcium hydroxide cancel out and I have grams, which is what I want. Okay, mathematically, I have just 2 sig figs right here. So this would give me 0.54 grams of calcium hydroxide when I multiply 0.0726 times 0.2, divide by 2, and multiply it by 74.10. Okay, so I will have 2 grams of calcium hydroxide. Okay, so let's do our next example. What is the molecular weight of a monoprotic weak acid if 0.5 grams of that acid is neutralized by 37 mils of sodium hydroxide? So I don't know what the acid is, so I'm just going to put in my generic acid. And I know it's monoprotic, so it gives me 1 hydrogen. Okay? So that means that if it's reacting with hydrogen or sodium hydroxide, I will make sodium X, right, with 1 water. So I'm going to have a 1-to-1-to-1 relationship because it's a monoprotic acid, 1 hydrogen. Okay, so here we go. I have both a volume and a concentration. I'm going to make that volume into liters. Okay, so I have 0.0370 liters of sodium hydroxide, and I have 0.2 moles of sodium hydroxide in 1 liter of that sodium hydroxide solution. So my liters of sodium hydroxide solution cancel out. I have moles. Now I'm going to look at my relationship. I have 1 mole of sodium hydroxide reacting with 1 mole of that acid, HX, right? Okay, so this gives me 3 sig figs. So this gives me, let's see, this gives me 7.40 times 10 to the negative 3 moles of HX. Now to find a molar mass, I need grams and I need moles. I was given grams, right? I want grams per mole. So could I take this 0.500 grams and divide it by the moles? 7.40 times 10 to the negative 3 moles of HX. That will give me my molecular mass. And when I do that, it gives me a molecular mass of 67.6 grams per mole. Okay, so I could actually figure out acids that have near that molecular weight and hopefully figure out what acid I'm dealing with. Okay, so there's some examples of quantitative neutralization. Okay, titration curves are what we use to figure out the amount of acids and bases that we have. So here we go. If I have a strong base, so if I have a strong acid and a strong base, I will have water and a neutral salt made. And that neutral salt will keep that solution neutral. So my equivalence point, and I'll get to where my equivalence point is going to be where the pH is 7. Okay? The equivalence point is where we get this pH curve. So we will get the pH along the y-axis. We will get the number of mils of acid added along the bottom. That equivalence point is what we call an inflection point. Okay, and that inflection point is where that slope kind of changes. You'll notice it ever so slightly changes it changes direction a little bit. In calculus, it would be the derivative, where the derivative equals 0. Okay, so we're not going to get into calculus, but you'll see on this curve that inflection point kind of is where that line changes from going up and then starting to come back down. Okay, a lot of times we will just look at in the middle of that really steep area. Okay, so, but if I have a really weak, so here's strong acid and strong base, that inflection point is right at the pH of 7. Okay, that's what we would expect in neutralization, but that doesn't always happen. So if we have a reaction where we have a strong acid with a weak base or a weak acid with a strong base. So here, let's look at this one over here. I've got a weak acid with a strong base. So if I have a weak acid with a strong base, that base is going to overpower it. So that means the inflection point will actually be at a basic pH because that base is stronger than the acid. If I have a strong acid with a weak base, my inflection point will be less than 7. Okay, because that acid will overstrength the base. Okay, overcome the base. You might think that all titrations must have an equivalence point at 7 because that's the point which concentrations of the hydrogen and hydroxide ions are neutral. But it's not the case. Some titrations have equivalence pH values less than 7, so that's when we have a strong acid with a weak base. And some have equivalence points with values that are greater than 7. That's when we have a strong base with a weak acid. These differences occur because of the reactions between newly formed salts and water, hydrolysis. We've already talked about hydrolysis, and you understand why those reactions happen. So this is just a little bit of quantitative neutralization and how we can figure that equivalence point out with either the pH or a color indicator. And I hope this was helpful. We'll see you later. Bye.